Hello everyone, today we are gonna solve a math problem. As you see, a squared plus p squared equals b squared, where a and b are positive numbers, so integers, and p is prime, and we have to prove that a is divided by 12, and also 2a plus 2p plus 2 is a square number. So first of all, let's rewrite this. Plus p squared equals b squared, and here we can rewrite this as p squared equals b squared plus a squared, or sorry, minus a squared, and this equals a b minus a times b plus a. And we just use the formula of the difference of squares, and so p squared equals this number times this number. We know that p squares can be rewritten as 1 times p squared or p times p. Because p is a prime number, so only divisors it has are p and 1, and so p squared has only those divisors. So from here we can say that either p squared equals a plus b and 1 equals b minus a, or in the second case we have that p for example equals a plus b and p equals b minus a. Or there can be second case which says that p squared is b minus a and 1 is b plus a. But of course this one is nonsense. It can't be, so just like that. And here from here we can see that a times b equals b minus a plus b equals b minus a, but this is also impossible because a and b are positive integers, so there we have only one case. Let's solve for this one. Let's rewrite this as p squared minus 1 equals a plus b minus b minus a, which is a plus b minus b plus a, and that's 2a. So here we're gonna do a manipulation. We will add both sides to p and 2. We get that this one equals p minus 1 plus 2p plus 2, which equals p squared plus 2p plus 1, which of course is p plus 1 squared. So we got that this sum is a square of some integer. So the second part of this problem is proven. So we proved this one. Now we have to prove the first one. So let's see. Okay, how can we prove that? Let's say that, yeah, we can maybe prove this one from this equation. So a is p squared minus 1 divided by 2. Every prime number can be rewritten as 12n plus some r, of course, where n is a integer, and is an integer which is equal or more than 0, and r is also an integer which is from 0 to 11. So if we want p to be a prime number, then r must always be 1. It can't be 2, because if, for example, r is 2, then p is 2, 6, and plus 1. And so we get that p is divided by 2, and it's divided by other numbers, so therefore p can't be in prime number. So r can be 2, also can't be 3, because 3 divides 12. It can't be 4, it can be 5, not 6, also 7, not 8, not 9, not 12, and 11. So we have only these 4 cases. Now let's see what we can do here. So if r equals 1, then p squared minus 1 divided by 2 equals 12n plus 1 times 2 minus 1 divided by 2, which is 4n squared plus 24n plus 1 minus 1 divided by 2, and which of course is there will be 12, so it will be 12, here will be 6n squared plus n. So we see that because of a equals this one, and this is divided by 12, therefore a is divided by 12 too. So, oh my, why doesn't it work? Okay, now we can solve for r equals 2 by 2. We'll have 12m plus 2. Oh, not 2. Sorry for mistake. Not 2, because then we have 1, and the next one is 5 minus. So we'll have here 5 minus 1 divided by 2. It will be squared plus something like 120n plus 24, because 5 squared is 25. 25 minus 1 is 24 by 2, and of course we can clearly see that this one is divided by 12. Now let's solve for r equals 7. This is 12n plus 7 squared minus 1 by 2. It's n squared plus 24 times 7n plus 48 divided by 2, and of course this one is also divided by 12. And finally we can solve for r equals 11. We'll have plus 11 all squared minus 1 divided by 2. It will be like that plus 24 times 11n and plus 120 divided by 2. And of course this one is also divided by 12. So we've shown that if P is written in this form and R equals these numbers, R have to be equal, R has to be either 1, 5, 7 or 11, because otherwise it can't be prime. So we've proven that in that case A is divided by 12. So therefore this problem is solved. Goodbye.